make a break in between, or and
yeah, you decide. You can decide. Sorry, I haven't told you this thing. You can decide either take a break or finish earlier.
Yeah. Okay. Sounds good. Yeah. So Jinwei, thank you for organizing this and giving me this opportunity. This is nice. I think it's quite timely because many people have thought quite a bit about representation theory of affine vertex algebras at admissible level, and things have been quite difficult. Things are still quite difficult, but there are a few things we understand better, and this is what I want to explain in these lectures. So today I want to present generalities and also motivate the whole thing. And the progress is mainly restricted to SL2. So this will be then what the next 3 days will be about. Yeah, anyway. So what's the motivation? Let's maybe start by standard construction of vertex algebra. So we are interested in vertex algebras in general, and I think you all have heard about vertex algebras. They came up first in the 1980s, and the first vertex algebras were associated to lattices and affine algebras, and they came about because they were symmetry algebras of conformal field theories. They were interesting for moonshine, etc. And since then, many people have studied vertex algebras, and there are a few standard constructions. Given a vertex algebra, how can you get a new one? And the first one, let me call it BRST, after as physicists call this, as BRST cohomology. So whenever you have a VOA, or better say a super VOA, and you have an odd field that has a regular OPE with itself, so, or more importantly, whose zero mode squares to 0, and then one can look at the homology of this VOA. So you just take the kernel of D naught, the D naught acts on V, take the kernel modulo the image of D naught, and this is a VOA again. And we have a very famous example of this, namely if we take an affine vertex algebra itself, a vertex algebra associated to a Lie algebra and a nilpotent element, then one has the corresponding quantum Hamiltonian reduction, and that gives a W algebra. So for example, the W algebra of the affine vertex algebra of SL2 is the Virasoro algebra. And then there are many others. So W algebras may be, after affine vertex algebra, the second best known family of vertex algebras. They just are realized as these homologies or cohomologies sometimes. So then the second construction is if we have a sub-vertex algebra, then one has the coset construction. So one can just look at the set of vacuum vectors for W inside V. That's the corresponding vector space is called W in V, the commutant of W in V, and it itself has a vertex algebra structure, again called the coset VOA, or the commutant VOA. A closely related construction is the orbifold. So if we have an automorphism group of our vertex algebra, then we can look at the subspace that is left invariant. This is called the orbifold, and it's again a VOA. So what else can we do? We can do an extension. So these first 3 constructions were looking at subalgebras and quotients of subalgebras. Extension is doing the kind of the opposite. Given a VOA, and a module for it, such that our VOA embeds in M. Then sometimes, in fact, very rarely, M can be given the structure of a VOA itself. Extending the one of V. And this almost exhausts our construction. We have then the simplest one is just if we take two VOAs, then its tensor product is also a VOA again. Okay, so these are the standard construction I can come up with, and now one can formulate a challenge. Namely, the challenge is find a VOA V that can't be obtained from an affine VOA via iterated standard constructions. And if you look at the literature, you will not find a single example of a VOA that cannot be obtained from an affine one. There's a famous conjecture called the Auger conjecture. So Auger found a small modular tensor category that looks like it admits an underlying VOA and is completely open how to construct it. In any case, many people have invested energy into this challenge, and to my understanding, it's completely open. I want to turn this around and say this is a motivation. In the sense, well, what are we interested in VOA? These are some kind of algebraic structures. Well, if you're not interested in these structures a priori, but they're representation theory. Representation theory is somehow well preserved under these constructions. So we should say, well, if every vertex algebra that we know comes from an affine vertex algebra via maybe a big sequence of these constructions, then it's probably quite important to know the representation theory of affine vertex algebras. And because they somehow sit on the top of the VOA hierarchy. Okay, so so this is the motivation for vertex algebras, and now we want to but we don't want to just look at vertex algebras, but we want to look at representation theory. So, and let me formulate a few questions, and before I do this, it's maybe nice if I define a module. I didn't define the VOA. The VOA definition is quite similar, but I'll define now a module for you. So let's call this module M is a vector space, and typically we are looking at C vector spaces. And in this vector space, we denote by this very same symbol as the module itself, together with a family with fields. So form a power series with coefficients endomorphism operators on our vector space, such that it satisfies a bunch of axioms. So the action of a field on a vector in our module is then a formal power series itself. And the condition is that it's in fact a long series. And in the VOA language, we call this the lower truncation condition. In representation theory, this is often also called smoothness, the smoothness of a module. That's two words that mean the same thing. Then we want the field associated to the vacuum to be just the identity. And the most important identity is the Jacobi identity. So it's formulated in terms of the formal delta distribution. So I don't know how much background you all have, and so I thought I will start by presenting a little bit of background on vertex algebras before going into all the fine structure. So this Jacobi identity can also be formulated in terms of correlation function, and it's some kind of a combination of an associativity and commutativity property of these fields, that they are products of fields if I acting on a vector in the module, if I that this product is in a certain sense associative and commutative, meaning if I swap the order of action of fields, it gives you different formal power series, but they can be somehow analytically continued from one to each other in a certain sense, which is the commutativity property. And from a technical point of view, it's most convenient to formulate this in terms of this Jacobi identity. Now, a vertex algebra, a vertex operator algebra always has a Virasoro subalgebra. The corresponding field is usually denoted by L of Z. So it's the field corresponding to the conformal vector omega. And these the modes satisfy the commutation relation of the Virasoro algebra at some central charge. Now, so you always want that to have, and you want your translation operator of the VOA to be the L-1 of the Virasoro algebra. So in particular, it acts as a derivative on fields. Okay, so I assume that most of you have seen it, and if you haven't seen it, this is then what you learn from this is that already the definition of a vertex algebra and then its modules is quite convoluted. So it's unfortunately always takes a long time to even introduce it. And if I just defined everything, then after these many hours of lectures, we would not have been much beyond the basics. So anyway, now one requires a few extra conditions that make the module structure nicer. And so first of all, we have an infinite dimensional Lie algebra, the Virasoro algebra acting. And so then it's natural to require that the module is somehow nicely graded by a Cartan subalgebra of the Virasoro algebra, which is just the subalgebra generated by its zero mode. So such a module then you then call a generalized module. So if M is graded, and here these Mn, they are L0 eigenspaces, and why not being as general as possible? So you require them to be generalized eigenspaces of eigenvalue n. So this is generalized, meaning this L0, this Virasoro mode might act nilpotently. I mean, it might be just here. This Mn can be decomposed into Jordan blocks. If you look at classical literature, this almost never happens, but roughly for the last 20 years, it has turned out more and more that most representation categories of vertex algebra admit modules that are generalized in the sense that one has generalized eigenspaces and not only eigenspaces of the Virasoro mode. And that this is important for this logarithmic conformal field theory. It is the feature of non-semi-simple representation categories, and it also this non-semi-simplicity is in fact what makes the representation theory that we are discussing both interesting and challenging. So it's yeah. Okay, so generalized is quite general. What else can we do? Now we call the module lower bounded if the L0 eigenvalue is lower bounded. And so lower bounded is nice because that means the conformal weight, the L0 eigenvalue is also called for conformal weight is lower bounded, and these are the types of modules one will have best access to. And what we will see, not this lecture and not today, but probably tomorrow, is that lower bounded are a good starting point, but actually, in fact, we will see this at the end of today, but we will see that most modules are not lower bounded for affine vertex algebras already. So it's, and then ordinary modules are those lower bounded modules that have in addition the really nice property that each weight space is finite dimensional. So usually you also require that L0 acts semi-simple on ordinary modules, but I decided to leave it out here. So this is a quick, just the definition of module and a few special types of modules. And now we can formulate a question. So now, what kind of question would we like to formulate? We would like to do some representation theory. So this means we choose a category, call it C. And of course, a category of modules for a VOA. And one usually puts some niceness conditions on it, for example, them being ordinary or lower bounded. But these conditions have to be chosen wisely so that you can do interesting representation theory. And once you choose your category, you ask a few questions. Well, what's the first thing you want to do if you want to understand representation categories of some algebraic object, some object of interest? You first want to simply understand what type of objects do we have. And so that means maybe the very first thing you would like to ask is, can I enumerate all simple objects? That's probably the most natural first question. Then the next thing you would, I imagine, ask is, well, do I have objects that are not direct sums of simple objects, and can I understand possible extensions between simple objects? So, for example, the natural next question is classify extensions of simple objects by simples in your category. And then finally, if you really would like to say I do understand my category well, then you would want to have a really good picture about all possible extensions, and that you achieve, for example, if you can classify all projective and injective objects in C. Note that in the examples of VOAs that we do understand well, projective and injectivity is usually the same, which is seems to be a property of VOA categories. Okay, so now this is the question we want to ask, and now we can ask what kind of general technology do we have? Well, we don't have any technology at all to classify extensions, or let alone projectives and injectives. This is always quite challenging. But simple modules, there we have a wonderful technique. So this is good. And to a vertex algebra, you can associate an associative algebra called Jiao's algebra. Sorry, I can't pronounce that correctly. Jinwei, can you say it once for me, the name?
Jiao's algebra.
Don't you pronounce it differently?
Yeah, we just said more quickly, Jiao.
Okay, good. Anyway, so it's a good technique, but it classifies simple lower bound modules. In general, it's not that easy neither to deal with the Jiao's algebra, but the Jiao algebra of an affine vertex algebra, of the universal affine vertex algebra, is just the universal enveloping algebra of the underlying Lie algebra, of the finite dimensional Lie algebra. And of course, representation theory of a finite dimensional Lie algebra. That's wonderful. That's a classical topic, right? You can just look it up. Of course, it's the question again, what type of modules of this finite dimensional Lie algebra you're interested in. And again, that can become arbitrarily complicated already for finite dimensional Lie algebras. But in principle, wonderful, right? Because it relates your modern problem to the classical Lie theory. Okay, now this is maybe the abelian question, and now next we would like to know more. Next question we would like to ask is whether our vertex algebra is a vertex tensor category. And so vertex tensor category that Jim Lepowski, E.G. Huang have studied, that there are other prominent names in this area. And so in the late 80s, there was a very influential paper by Moore and Seiberg. What was it? The axiomatics of conformal field theory? I forgot. Yeah. Anyway, they formalized what they understood. They formalized their understanding of rational conformal field theory, and essentially that was the definition of a modular tensor category. And then Huang and others, they proved that indeed that a category of modules of a vertex algebra satisfying certain conditions naturally has a structure of a braided tensor category. So it's a tensor category, it has a tensor product, it is associative, and it's also commutative up to isomorphism. Very nice. Now, so this theory is, I should also always say the name, so it's due to Lepowski, Zhang, and Huang very much. So, and this question really means your given category of VOA modules has to satisfy two important things. So these two are the most important conditions for having vertex tensor category. So let me write them down. So you need a category such that for any pair of modules, well, what do you need? If you want to have a tensor product, you need that the tensor product exists. So this means for any pair of objects in your category, there exists an object that you call M tensor, or maybe box times n in your category, and an intertwining operator, so a field that maps vectors in M tensor. Well, that intertwines from M and N to this M box times N, such that it satisfies. Well, it satisfies what? How do you introduce a tensor product if you do your linear algebra first your course? You say this is defined by the usual universal property, and so here the tensor product of UA modules is defined by the same universal property as the vector space tensor product, or whatever you prefer, except that it is realized by intertwining operators, by fields again, and so that yeah. So let me just state the universal property. So this means that what is it? This M box N has the universal property that for any module R and any intertwiner from your modules Mn to R, that we have a unique map, in unique homomorphism from our tensor product to R with the universal property that your intertwiner I is just the composition of the universal intertwiner with F. And what's the second property you want? It turns one might wonder what is difficult in establishing a tensor product, and it turns out the braiding is a more or less automatic property. That means the commutativity of the to-be tensor product, but the associativity is a complicated thing. It has to do with and so let me formulate this once, because it's really the most important property. So what is associativity? Associativity is we take the tensor product of 3 modules, and we want to compare just the order in which we take the product, right? We can take first M with N, and then the answer with R, or M with the product of N and R. And associativity says that taking these two products should be isomorphic. And for the VOAs, well, this isomorphism, better this family of isomorphism, is called associator. And you want to have a whole family of associators depending on the insertion points. So and the associativity property is then that we write now down the tensor product in terms of intertwining operators. So M denotes a vector in the module M, and lowercase n, a vector in the module n, and r accordingly. And what you want is that this composition of the associator maps the composition of these intertwiners to this one. And then you have also certain convergence conditions, which I'm not stating now. The point is that the hard thing is to show that you have this associativity isomorphisms. And now the question is, how do you ensure that these associativity isomorphism hold? And for this, finiteness conditions of modules come into the play, because so what you do is you can express this you can evaluate these expressions like this composition of intertwining operators with a vector in the dual of R, and then it will just give you a certain function in the insertion points, which one should call a correlation function. That's what the physicist calls it. That's what one calls it. And now the associativity follows if these correlation functions are nice enough. And that is ensured if they satisfy nice enough differential equations. They have to be solutions to nice enough differential equations. And that you have such differential equations ensured by finiteness condition on modules. So it turns out to have this associator, finiteness conditions are so important. And this finiteness condition go under the name C1, C2 cofiniteness. So let M be a lower bounded module. One calls it Cn cofinite if a certain quotient has finite dimension. Quotient by a certain subspace, the Cn subspace, is finite, whether the Cn subspace is the subspace that you get by acting with the minus n modes of the VOA on M. Okay, and now the good vertex tensor category theorem that VOA theory has is due to E.G. It says the following: let V define something, satisfy standard niceness conditions. So it is integer graded by conformal weight, non-negative integer graded, with the top level just being the vacuum. This VOA, you want it to be its own contragradient dual. And so these first three conditions are satisfied for many VOAs. This is not a big deal. The important thing is that you want V, the VOA itself, to be C2 cofinite. Then the category of V modules is a vertex tensor category. So VTC, vertex tensor category. And in fact, this category of V modules, every module is already ordinary in the sense I define it. So this means conformal weights. Every module is lower bounded, and conformal weight spaces are finite dimensional. But they might be generalized eigenspaces. So L0 might act importantly. And And then the most famous class is probably if the category of V modules is in addition to C2 cofinite, also semi-simple, then the VOA is also called rational or regular or whatever. And in that case, the vertex tensor category is in fact an MTC, a modular tensor category, a rigid, braided, finite, semi-simple tensor category. The thing that a topologist, a low-dimensional topologist uses to compute invariance of three manifolds and so on. And the thing that a physicist likes to use for three-dimensional topological field theory. So the thing that has been of classical interest in a lot of cases. Okay, but we want to go beyond this rational world, and we want to go beyond the C2 cofinite world. And in fact, if you so vertex algebras associated to an affine algebra, affine VOAs, they come with a level, and it turns out a VOA is C2 cofinite if and only if the level is a non-negative integer. And if it is C2 cofinite, it's already rational. So it's so that in particular the set of affine vertex algebras to which this theorem applies is a set of measure zero within the modular space of affine vertex algebras. So in particular, we want to go beyond. I mean, if I wanted just to talk about a positive integer level affine VOAs, I could have given this lecture 40 years ago. Right? This has been known for a long time. So we want to go beyond this, and so let's see what do we need. So let's first. I'm now giving you a very useful result by Miyamoto, and it's concerned with the first condition here of having a vertex tensor category. So here, if you want the category to be a vertex tensor category, so you in particular need the tensor product to exist and to satisfy the universal property. So what that means is you have to choose your category wisely, that with any two given modules, the universal intertwiner is also in that category. And Miyamoto gives us a very good statement. He says the following: if M and N are C1 cofinite, then the same is true for its tensor product. It's meaning what I'm. Let me also, maybe I'm a little bit sloppy. What I mean here is that with if you have a surjective intertwiner of type M, N, M and N to R, and M and N are C1 cofinite, then R is C1 cofinite as well. The image of a intertwiner of C1 cofinite modules is always C1 cofinite. That's what this statement says. Okay, and this statement was also the starting point, or maybe the most important input to discussions that Jinwei and I had a lot. It was extremely helpful for us because what we desperately needed, I mean, not only we, but when one needs a criterion, I mean, one wants to have a vertex tensor category, right? One wants to have an answer to the question, where am I? To this question here, beyond just the C2 cofinite VOAs, beyond this extremely special class of VOAs. So you need a good criterion for this to work. And so what can we say is so the C1 cofiniteness is good because it guarantees two things at the same time, namely closure under tensor product. I mean, it guarantees that the tensor product of two C1 cofinite modules is C1 cofinite, and it also gives you differential equations that have the good properties. So it turns out that if your category satisfies a few properties with so let me write them down. So the very important property, every object is C1 cofinite. Then and then a few standard properties. Of course, you want your category to be abelian and a finite length, and you also want it to be closed under the contragradient dual. So these are properties that are very natural. What else? Of course, we need closure under tensor product. But for example, if we simply take the category of all C1 cofinite modules, then it's automatically closed under tensor product by Miyamoto. Then the only question is it in fact an abelian finite length category that is closed under contragradient dual? These three properties in the middle are unfortunately not totally are not automatic. Anyway, it turns out these conditions ensure that you have a vertex tensor category. And I will give you a few examples of that very soon. So I actually plan to spend roughly the first lecture on motivation. I'm a little bit faster even, which surprises me. Usually I'm slower than I expect. Anyway, so I wanted to give you a motivation tour together with the questions that are the guiding question for myself and those I work with. We have here Robert, Flora, Jinwei in the audience. These are definitely guiding questions for us. So the last question is, if we already know that C is a vertex tensor category, and we can only know that C is a vertex tensor category if we already understand it as an abelian category quite well somehow, then we would like to ask questions about fine structure. And so what is fine structure? For example, you would like to know what is the precise tensor product of two modules. That would be then the fusion rule. Or one thing that one really likes, and one would like to know whether the category is rigid if we have duality, and the duality, so that we maybe get a ribbon category, and right, this is what, for example, topologists again need. Turns out, if you look back, beginning of the 90s with these invariants of knots and links and three manifolds computed out of modular tensor categories, one then very soon asked what are the key properties that you need in order to compute such invariants to do topological field theories. And the semi-simplicity is not the key thing. The key thing is that you need to have these dualities. That's most important. And then you of course need additional good property, but that's the key thing. By the way, last week or 2 weeks ago on the archive, there was a really nice paper by Nathan Giat who introduced Hermitian TFTs based on Hermitian ribbon categories. And these are categories that are neither semi-simple nor finite, very far away from those. And these are categories that look extremely similar. The VOA categories I'm going to discuss in the coming lectures look extremely similar to what they have. And it looks like really, for example, these admissible level affine VOAs, they should produce categories with which you can do nice topology. Okay. Yeah, I stop with the motivation. So what I said that affine vertex algebras, so vertex algebras coming from affine algebras, are important because nobody in the literature is aware of a vertex algebra that is not coming from an affine vertex algebra. And then I gave an outline about the key question representation theory. So the key questions you want to ask is, first, the abelian key question is you decide wisely what kind of category of models of UA choose you want to study, and then you want to understand it as an abelian category, and ideally then also as a monoidal category, all its details. And then usually, in fact, you will find quite a few nice applications. Okay, and now I come to affine Lie algebra. So that's the algebra underlying an affine vertex algebra is an affine Lie algebra, and quite a bit can be formulated purely Lie theoretically. So I will be mostly, almost completely concerned with algebras, but I will here at the beginning at least state a few things for super algebras as well. Just because it doesn't make a difference, and it turns out that super algebras are more interesting than the algebras in many respects. Much more difficult, but also much more interesting. This, as you know, that goes often hand in hand, right? What is easy? Exciting things are rarely easy. So finite dimensional, simple, the super algebra. Maybe usually you would take a basic one. You can also allow GLN/n. It behaves in many respects like a simple one. And then what else do you have to do? You have to fix a bilinear form. So, that is non-degenerate. That's then invariant. So it has to respect the Lie bracket. Bilinear. It has to be symmetric. So if it's super, you call it supersymmetric. And if it's super, you also want it to be consistent. Consistent means you want the pairing of an odd with an even element always to vanish. Okay, and then and now we fix a bit of standard data. So I just fixed now the standard details about the affine Lie algebra. Maybe recall a few things for you. It just turns out it turns out we need a very special type of operation, and you can only understand what it is if I introduce the data here carefully enough. So what's next? Next we fix a Cartan subalgebra. So its dimension is the rank of our Lie algebra. Then we fix a set of positive simple roots. What else we need then? Usually we need a good identification of a Cartan subalgebra and its dual. So the dual here is denoted by H star. And we can do so because we have, so we denote this identification by nu. And it's just the map that maps H to this linear map from H to C. And now we normalize kappa in the usual way. So this is the usual normalization for Lie algebra. And for Lie superalgebra, what you do is the following. The Lie super, I only say that in words. The Lie superalgebra, except if it's always P1 to N, or always, I mean, the Lie superalgebra will always decompose into a simple, the even subalgebra of the Lie superalgebra will decompose into a simple Lie algebra plus plus a reductive one, and not uniquely. But anyway, you choose such a decomposition, and then you fix your bilinear form that the long roots corresponding to this simple subalgebra have norm 2, which is usually really just a choice of a sign and a normalization, of course. Anyway, for the co-roots, they are defined also as usual. The co-root to alpha satisfies this property. And now we have 4 sets. We have a set of simple roots, and these span the root letters. Then we have the simple co-roots. Which span the co-root letters. And so on. We have the fundamental weights and co-weights. So the fundamental weights, what sometimes a bit confusing, they are the natural duals to the co-roots. So they are pairing with a co-root is their natural duals with respect to our bilinear form. And so then we have the corresponding weight letters. Which I denote by P. And finally, we have the fundamental co-weights. Which are the natural duals to the roots. So this means they satisfy they are orthogonal to the, I mean they are dual to the.
So here your fundamental weights are in H, right?
The fundamental weights are in H exactly, and the co-weights in H dual.
Okay.
If anybody has a question, just unmute yourself or write in the chat. I have the chat open on my computer, so I see that if you write, then I will just stop when it's convenient for me and say something. Okay. Now, these are just here a few standard basics about Lie algebra. And now if we have a Lie algebra, then one wants to affinize it. So what do we do for that? Then we take now, we take the loop algebra, and this loop algebra allows for a central extension. So K here is a central element. And then whenever you centrally extend, you also like to add a derivation. This is the effinization. The commutation relations are given just by the commutator of the underlying finite dimensional Lie algebra. The exponents of t add up, and then you get an additional possible term coming with a central element. And it comes with the pairing of x and y. Now, if you look at vertex algebra literature, the derivation is very often omitted just because you can identify it with the Virasoro zero mode or with minus the Virasoro zero mode better. Now, the Cartan subalgebra extends then by adding the central element and d, and the and then the bilinear form as well. Why don't I just repeat this? So the central element and d, both of them are orthogonal on your original Cartan subalgebra, and the only new pairing that you get is that pairing of k and d. And then our identification of Cartan subalgebra that's dual, the nu extends accordingly. So why did I all introduce this? I thought, first of all, it's maybe good to recall all this. We are interested mainly simply in this affine Lie algebra, G hat. What we will do is we are interested in representations of those, and we are interested in representations where this k, this central element, acts as a fixed scalar, the level, because these are then representations also of the corresponding vertex algebra. And now we are also interested, and it's good to start with the affine Lie algebra because it already gives you for free a zoo of new modules. And they come, what can you always do is if you have an automorphism of your underlying structure, so an automorphism of your affine Lie algebra, then you can change your action of the Lie algebra on a given module by this automorphism. One says you twist it by the automorphism, you get a corresponding twisted module. So and it turns out this for the VUAs, this gives an enormous amount of new modules. What kind of automorphism does the Lie algebra have? Automorphisms coming from the so for the affine Lie algebra, it's automorphism coming from affine Weil translations from the translation group of the Weil group, or better said, you have something like an affine Weil translation. Labeled by elements of the co-weight letters. So we take here in lambda, something in the co-weight letters, and alpha in the dual of the Cartan subalgebra of the affine Lie algebra. Then one has the affine Weil translation that maps alpha to alpha plus let me write down the formula. It's a little bit lengthy. This formula is, this Weil translation are so important for VUA theory because they induce automorphisms called spectral flow automorphisms. So this name comes from physics. The physicist calls the the set of modules of a conformal field theory, the spectrum, and the spectral flow automorphism is an automorphism that flows through the spectrum, right? It changes the modules. And so it's called, then it's also labeled by the corresponding coweight, by the corresponding element in the coweight lattice. And let me tell you how it acts on generators of the affine Lie algebra. So it maps E alpha times t to the n. It changes the exponent here of the t to the n by an integer. And depending on what element I change. So what do I mean here by E alpha? I mean an element in the change any element except h times t to the 0 will get shifted by a multiple of the central element. The central element is left invariant, and the derivation is shifted by an element in the Cartan subalgebra corresponding to the coweight. Right? The coweights are in the Cartan subalgebra and a multiple of the central element. So what's the important thing of this? It's very important is that it changes here the moding of the modes of the affine Lie algebra, and that has the effect that if you twist a module by this automorphism, you start with a lower bounded module, then well, it won't get mapped to a lower bounded module. Another way to say this is this Lie algebra has a horizontal subalgebra, the subalgebra of 0 modes. And this automorphism doesn't leave this Cartan subalgebra and this horizontal subalgebra invariant. This means under this automorphism, the horizontal, you get a new embedding of your horizontal subalgebra in the affine Lie algebra. And the effect is then if you twist modules accordingly, it will map modules that are nice, lower bounded, and well understood, maybe to modules that follow in the generalized pi type that I presented, but nothing smaller. Okay, so let's go to categories, because this is where we want to go to. These lectures will be a representation theory. So categories. We are interested in G-hat modules, and now we give it a few names. So we call a module smooth if it is smooth. So smooth means for every x in the horizontal subalgebra and the Lie algebra, x times t to the n annihilates a given vector as long as n is sufficiently positive, sufficiently large. This is the affine Lie algebra analog of the lower truncation condition on the VOA side. Now, moreover, one associates to a module a spectrally flown module. The spectral flow twist of m by lambda, by the lambda and the coweight lattice. So what does it do? This is it's an isomorphism. Or, we have the underlying vector spaces are the same. This isomorphism you call sigma lambda star. So it maps M to the vector sigma lambda star of M. But the action of an element of the affine Lie algebra is twisted. So it doesn't act in the usual way on sigma lambda star of M, but it acts by the automorphism, and in fact one takes the convention that it acts by its inverse. Its inverse on M. Okay. Now this spectral flow, definitely it doesn't map lower bounded modules to lower bounded modules, at least not in general. And for positive integer levels, for this modules of the simple affine VOA it does, but otherwise it does not do that, or extremely rarely at least. But it has some nice properties, and they are actually obvious. For example, they preserve smoothness. And that's good, because smoothness is the, it turns out a module of the affine vertex algebra, of the affine Lie algebra, is also a module of the affine vertex algebra if it is smooth and if the central element acts by the correct number. So smoothness is the condition. And moreover, this spectral flow is exact in the sense, if I have a short exact sequence, then its image under spectral flow is also a short exact non-split sequence. Good. And the next vocabulary, we say a module has level k here a complex number, if the central element is equal to the level times the identity on the module. Okay. Now, what did I say in the motivation part? So maybe 45 minutes ago, I said the first question you want to ask if you want to do VOA.
So Thomas, may I interrupt
Yes.
you? Okay. So here your M is just an ordinary module, or no question, no restriction on that.
No restriction. No.
Just the admissible, or
it is
that's a generalized module.
Just a generalized module. Yes.
Okay.
Yeah.
Okay.
Of course, from now on I will restrict to smooth modules, because non-smooth is not VOA.
Yeah. Here is smooth.
But yeah. No. Good question. So let's at the very beginning, I said if I want to do a representation theory, I should probably be aware of the possible categories that are there, and which good conditions and which maybe not so good conditions they have. And then this is I mean, you're already asking, do I restrict to ordinary modules? Well, we will see. Maybe yes, maybe no, maybe no.
Yeah. But here, generalized module, I think it's reasonable, right? Yeah.
Yeah. It's
it's good. Yeah.
Can you say it again?
I mean, here you just consider the generalized module with the smooth condition is good, right?
Yeah. I study with most general, of course, because I only hurt myself if I restrict. But then, one has to see what conditions are, what kind of restrictions you better impose, because otherwise it will get out of hand. So,
okay, thank you.
Right. So let me define a few categories now, which then will also maybe also clarify what you want to know. So we'll just give it a few names. So maybe this one I will also call the big category, because it's the biggest one I will talk about. So it's the category of weight modules. So what are these? These are finitely generated. And you will see it's not the biggest possible module category. Finitely generated. Smooth is necessary, because otherwise it won't be your A module. Smooth. Weight modules. At level K. With finite dimensional weight spaces. So let me be more precise what I mean by this. I explained what finitely generated is clear. I said what smooth means and what level K means. So by finite dimensional weight spaces, we mean every module has a decomposition into weight spaces. So here, lambda, this is a usual weight in the Cartan subalgebra, and this is conformal weight. We require that these bi-graded weight spaces are finite dimensional. But we don't require what do we require? We require here that the Cartan subalgebra acts semi-simples. These are really weights. By the Virasoro zero mode, it only needs to be a generalized eigenspace, right? So here, so here these are two restrictions, namely that this this bi-graded weight space is finite dimensional is a restriction. And it's a restriction you kind of have to do, because if you look at representation theory of finite dimensional Lie algebras, then we can do SL2, and it turns out modules have finite dimensional weight spaces, but already at SL3, already at rank 2, you have modules that indecomposable modules that have infinite dimensional weight spaces, and it's extremely hard to understand these types of modules. So we don't really want to go into a topic where the finite dimensional case is already too hard somehow. Another point for this restriction is if we don't require this finite dimensionality in this sense, then there's no hope at the moment to get a tensor category structure. And anyway, I will call this the big category, and the big category will be the main object of interest, but it's very instructive to have a sequence of smaller and smaller and smaller categories that of course also get nicer, nicer, and nicer. So let me present the subcategories. Let's call this here was the big one, and then the first subcategory that we look at, we give a sub-index greater equal to 0. And so this is the subcategory of lower bounded modules. So in particular, these are the type of these are the type of modules you have access to with standard Lie theory techniques, because these are the modules that essentially come from the finite dimensional Lie algebra. Then next, we take the subcategory of lower bounded modules that are in the category O. So and then the last one is the one that you mentioned, the ordinary modules. And well, you can't. I can't put an O again for ordinary, because then I would have two O's and we wouldn't know what it means. So they get a subindex KL for Kasten and Lustig, because they did so much work on this category, on exactly this category. They showed that this category is a braided tensor category, and as such equivalent to the corresponding category of the quantum group. And here this by VKG, I mean the universal affine VOA of the Lie algebra G at level K. And now if we have a quotient of that, then we denote by V tilde KG weight mod dot. So the dot stays for either nothing, lower bounded, ordinary, or Kasten-Lustig. What are these then? Then these are the modules for the universal VOA of this type, of the type dot, that are in addition also modules for the quotient. And we will be interested in the simple quotient, which I denote by an L. Okay, so let me spend the rest of the day, well, of the lecture, maybe it would be the rest of my day, maybe, telling you a little bit what we know about these categories, in the special case that we can take the simple VOA and we choose this K, this level, to be special. So what does it mean, special? So let's first denote by H, check the dual Coxeter number. By H, the Coxeter number. And by R, check the laicity, the lacing number of G. So then one says that K is admissible if it's a special number of a special type. It's a rational number. And in fact, if you shift it by the dual Coxeter number, it's a positive rational number where P, the numerator, is large enough in this sense here. depending on whether the denominator is co-prime to the laicity or not. And now, why do you restrict to this? Well, so it turns out the following. First of all, one can ask, when is this universal affine vertex algebra itself already simple? Well, this depends highly on the level, and it turns out if you choose this level to be generic, then it will be simple. So what does generic mean? Generic, all irrational numbers are generic. It will always be simple. If you take the level, on the other hand, rational, then it depends the answer depends very much whether you are on which side of the critical level minus h check minus the dual Coxeter number you are. If you are more negative, then the universal one is already simple, but representation theory is still quite tricky. And if you're on the other side, the positive side, then the universal one is not simple. You take the simple quotient, and taking the simple quotient means your module category, your category of modules will become much smaller. And most rational numbers that are larger than the critical level are at admissible levels, and those are the ones one has best access to. So the admissible levels are interesting, and one has access to them. So if there are also positive, rational levels larger than the critical level that are not admissible, they're extremely hard to study. So yeah, so what can we do? Okay, and now let me present what is known in general. Then you'll also hear the names of those people who have done important work. So, and I'll start from the bottom to the top. So let's recall what kind of categories I introduced. I introduced 4 categories. The big one is just weight modules. So I require some finiteness condition on weight spaces so that it doesn't get completely out of hand. But for example, no lower bounded condition. And so this is a very big category. And in particular, already for the classification of simple modules, no technique a priori applies. The second category is the category of lower bounded modules. So for that's the category where, for example, Jou's technique applies to. Category O is, well, what representation, what people in Lie theory usually study. And then Kashan-Lustig is category of ordinary modules. That's definitely the nicest category. And now and it's the smallest one. So surely most is the Kashan-Lustig category will be best known, and then we will have less and less knowledge. So what do we know about Kashan-Lustig? First of all, we know it's a semi-simple category. This is a theorem of Tomiyuki Arakawa. Then it's a vertex tensor category, and this statement is probably one of the main starting points why I'm giving the talk here. So Jinwei was visiting me. How many years ago, Jinwei?
I think that's 2015.
15, so 7 years ago.
7 years.
That sounds about right. And we were chatting, and was at that time beyond C2 cofinite VOAs. One more vertex tensor category, namely the category of Fock modules of a Heisenberg VOA, which is so trivial that you can simply check that associativity is satisfied. So We talked there, and then we noticed that really the Kasan-Lustig category, the category of ordinary moduli at admissible level, it looks like the positive integer case. It is the semi-simple category. Simple modules are parameterized in a very similar way, and there's no reason to believe that this is not a very nice vertex tensor category. So you should be able to show that. And yeah, so and then we slowly improved our technology until we noticed that that really the C1 cofiniteness is the key thing. And where did we notice this? This was in our paper with Flora about the Virasoro algebra. So that was the next important thing. Okay, what else did I say in my questions? You want to classify. So if you want to understand a category, you want to classify simple objects. Okay, then you want to classify extensions. Well, here, very good, semi-simple, no non-trivial extensions. We're done with that. In particular, every object is projective. So then you want to know whether you have a braided tensor category structure, also positive. And then now you want to understand fine structure like fusion rules and rigidity. It turns out both of them doing certain tricks, going to W algebras you can compute. And for example, I mean, you can compute fusion rules and you can prove rigidity, but only if you have enough information. So at the moment, it's in type A, C, D, and E, and in fact also OSP 1 to N. So OSP 1/2N is the only Lie superalgebra, simple Lie superalgebra that is not a Lie algebra and that allows for a positive in a bilinear form, and that is, and in fact it behaves in many respects like a Lie algebra. In fact, it behaves in most respects like a type B Lie algebra. And in fact, everything I'm saying here, the semi-simplicity and the vertex tensor category statement and the rigidity also holds for OSP 1/2N. That's quite nice, and that's a relative recent result of Naoki Genra, Andy Linshaw, and myself. Anyway, I will not say much more about Lie superalgebras. What about the category O? So now modules are still lower bound. They still have a highest weight vector, but top level does not need to be finite dimensional. They are not necessarily ordinary anymore. What do we know there? It's again very nice in the sense that it's a semi-simple category. And again, thanks to Arakawa. But what else? So can it be a vertex tensor category? Well, the answer is no, because it's not closed under tensor product. And for that you need an example. So David Rideau definitely computed one. Physicists had statements along these lines before. I think Matthias Gabadil was the first one. Anyway, one knows from experiments, from examples, that it can't be closed under tensor product, and so they don't even have to look further concerning vertex tensor category. And this non-closure is related to something else. Let me write it down. So what else can you do if you have modules? Well, you like to assign to it a character. That means a graded trace. And this graded trace, then you usually hope that they converge, for example, to nice functions on the upper half of the complex plane, and maybe then as such enjoy nice modular properties. So, and it turns out indeed the graded characters of objects in the category O at admissible level, they are formal power series that converge in certain domain, and they can be then analytically continued to meromorphic Jacobi forms. So this means analytic continuations of characters enjoy nice modular properties, nice vector valued modular forms. And whenever you get a finite dimensional vector valued modular form, you take the corresponding modular S-trace matrix and you compute the corresponding Verlinde formula. And it turns out it doesn't make much sense. So what do I mean by this? Let me just explain it in a few words. So you have this category O is a finite category. It has a finite number of inequivalent simple objects. So to each such object, you can associate the corresponding graded trace, the character, and via analytic continuation, you can identify it with a meromorphic Jacobi form. And then under modular transformation, you get these characters, their linear span closes. And so in particular, the transformation that maps the modular parameter tau to -1/tau it's called the S transformation, gives you then a corresponding matrix called the S matrix. And the Verlinde formula in a modular vertex tensor category for rational VOA tells you that this modular S matrix is the very same thing as the modular S matrix that you get in the tensor category. The modular tensor category is called modular because it has a modular group action. And these two things up to normalization are the same thing. But the categorical S matrix determines also the fusion rules. And that's then called the Verlinde formula. So based on physics grounds, and anyway, usually things are very nice, you expect that this Verlinde formula does not only hold for rational VOAs, but much beyond. And so it's somehow disappointing that for this category O, this doesn't work. But in fact, why should it work, right? If David is already telling us that this category is not closed on a tensor product, so how can possibly be there a good Verlinde formula? I'm not sure whether I'll have enough time, but I could say more on that. We'll see how the next lectures develop. Maybe say in a few minutes what I can present, and I'm not sure whether 8 hours will suffice. Okay, so we go one step bigger. So we go to the category of lower bounded modules. What do we know there? So I should also have added years. So everything I presented so far is not that recent, except our paper, Jinwei, was maybe 5 years ago now, something like that. So it's here for the lower bounded ones, the classification of simple modules is done by Kazuya Kawasetsu and David Without. And it's maybe 3 years old. It's fairly new, definitely. One result that is not that easy to find in the literature because it's a small remark in one of Tomiyuki's papers is that every lower bounded module admits its top level admits a central character. So in particular, L0 acts semi-simple. And yeah, and what else? So, well, one more really good thing is known, and this is a 20-year-old result of Futoni and Silke. It's not exactly phrased like I'm phrasing it, but it's a very easy consequence of their theorem. So it says the following: if we look at the big category, right? I call it big category. Then as long as we look at a simple module, and as long as our level is non-zero, we'll never look at level 0 anyway, then the following is true. There exists a lambda in the co-weight lattice with a property that the spectral flow twist of the simple module is a lower bounded module. This is excellent, right? Because if you, so this means you can say the combined result of cover sets without Photoni and Silke says that one has a classification of simple modules in the big category. Really nice. So this means the very first point of my list of questions is solved. And now, what was the second thing I asked about the abelian category? I then asked, well, okay, very nice that one can maybe classify simple modules, but you definitely also want to understand extensions, you want to understand projectives, etc. And so what is known about that? And we have a paper coming, and much about my lectures will be about this paper. I hope that this paper will be online very soon. It should be. It is written. Maybe we just want to add more statements about relations to quantum groups, but maybe we shouldn't. So this is a general theorem about extensions. So it says the following: let A and C be two modules. You want them to be almost simple. So what does almost mean? It means that every submodule almost simple means that every let me write it down. Every submodule intersects the top level. Trivial, so in particular, A and C are both lower bounded modules. So almost simply and specific lower bounded modules that the physicists, actually this was Alyosha Semikhatov who introduced this term. So relaxed highest weight modules. People are often complaining about this terminology just because it has the name highest weight in it, and it does not have a highest weight vector. So anyway, let me tell you what these are. These are lower bounded modules, lower bounded weight modules that are generated by a single vector, the relaxed highest weight vector. And what time do we have? Yeah, I think I will start the next lecture by telling you, by giving you a complete list of relaxed highest weight modules of the finite dimensional Lie algebra SL2, so that you get a feeling of what they are. So what is this? This is a no extension theorem, essentially. So, and it goes into two cases. If the conformal weight of the top level of A and C coincide, so they have same conformal weight, then one has the statement that a short exact sequence, an extension of a C by A, or maybe not as an extension, so this short exact sequence splits if it splits on the top level. And the second statement is if the conformal weights are different, then there is no extension, it always splits. Then, so if the conformal weights of the top levels are different, then any short exact sequence of this type splits. So this theorem tells us, well, at least in the category of lower bounded modules, the problem of studying extensions is a problem of the horizontal subalgebra. That's what the statement tells you. That's very nice, right? Because it relates to something one can do. Okay, and this exhausts everything that is known on the level of general results about admissible level affine vertex algebras. So let's look over it a little bit. We have 4 categories going from top to down. The big category of weight modules, which lack boundedness conditions. The thing one usually looks at, lower bounded modules, which has then subcategory of category O modules, highest weight modules, and then Kashtan-Lustig ordinary modules. The category of ordinary modules is wonderful in the sense that it's semi-simple, tensor, rigid. I should also say this rigidity should always hold. It's just at the moment, it's not always yet proven. So I think Robert, yeah, anyway, people are thinking about it, and it's probably just a matter of time that this rigidity will be settled. The category of O is a little bit bigger. It's from the abelian point of view as nice, but it's not closed in a tensor product. In fact, another tensor product of 2 modules in the category O, modules that are not even lower bounded will appear. So they will. It in effect tells you if you want to have a vertex tensor category, and if you want to allow for one module that is not not in Kashtan-Lustig, not ordinary, then you already have to go to modules that are not lower bounded. You have to go to the big category. Yeah, and then the lower bounded but then at least thanks to Kawasatsu, Redoubt, Photonic, Silke, we have classification of simples all overall, and there's good vanishing criteria or good criteria for extensions in the category of lower bounded modules. And now one wants to do the whole deal. This means one wants to not go on, one wants to classify extensions, classify projective models, classify injective models, and prove that one has a vertex tensor category. Now, what is the problem with the vertex tensor category? Well, we have 2 theorems that allow us to deduce the existence. Huang's C2 cofiniteness one, well, that is completely useless here because we are not dealing with a C2 cofinite VOA. And the Jinwei and my theorem for C1 cofinite modules. But C1 cofiniteness is a criterion on lower bounded modules. It doesn't even apply to the big category. And even on lower bounded modules, what's the C1 quotient of a lower bounded modules? It's exactly the top level. So that means a module of an affine vertex algebra is C1 cofinite if and only if its top level is finite dimensional, which is if and only if it is in KL, if it's an ordinary module. So this means that the category of modules to which our existence of vertex tensor category theorem applies is the smallest one of the four. That's quite bad, right? Anyway, I'll tell you how to overcome this issue. And but first I have to do the classification. And in fact, I can't really overcome this issue unless I do the very simplest case. So from now on, we restrict to the simplest case. That's already quite hard. And but at least I'll be able to tell you a lot. So yeah, why don't I? I could also go on, but Jinwei, shall I go on?
I think it's just good for today. Thank you. That's actually really nice. So maybe somebody can have some question. If the yeah, but let's first thank Thomas.
Thomas, thank you very much. Very nice.
You're welcome.
Yeah. So I have a question. So you talk about the result of tuning, right? So you see M is VKG weight module, just simple. Then we can find the lambda such that sigma lambda star M. So I mean the condition is so little. I mean just a simple weight module. They can find the lambda such that it's
the statement is the following: if I have a simple module, then the simple module must already be a spectral flow twist of a lower bounded module. So what it means is the following: what it means is you can also phrase it differently. Every simple module is a lower bounded with respect to a choice of a horizontal subalgebra, I mean a triangular decomposition, and all these are ones. Yeah, you can phrase it in different ways. But it's yeah.
So let me think about it. Okay.
Yeah, you can. Yeah, one has to think about it. This is definitely not obvious, but what you can also try to construct modules, and well, you will simply not succeed to construct a simple module that doesn't have this property. It's
because it seems to me that we can, not a lower bounded. Of course, it's not a higher bounded. Just let me think about it.
Yeah,
okay.
I can also tell you the difficulty about this. I mean, what this statement tells you is.
So it's a very nice result. So it's very useful, right?
It's extremely useful. But yeah, it tells you on the level of simple modules. On the level of simple module, everything is classifiable because a lower bounded you can classify using Joule's algebra, and everything else you get via this theorem. But what's the problem with it? The problem is this theorem totally fails for indecomposable modules. And what happens is there are extensions of simple by simples that.
So here simple is very essential, right? Yeah.
The simple is exactly.
Yeah.
So I always have problems with the pen. Anyway.
Okay. So.
Yeah. So, but to now we run into the problem if you want to. I mean, usually you think about it. here the x-axis is our the weight direction, and then the y-axis is conformal weight. And so lower bounded moduli would picture like this. And if you do spectral flow, what it will do is it will tilt this type of modules. So maybe a spectral flow twist would look like this.
Mm-hmm.
Now the problem arises. Now you want to understand possible extensions, and the previous theorem tells you, well, okay, as long as I'm just stay with lower bounded, it's a problem of finite dimensional leaf theory. That's fine. But it could, of course, be that I have extensions between modules that are differently tilted, and now you need to find technology to find these extensions, or to exclude their existence. And this is quite challenging, and of course also very interesting.
Okay.
So and this is where I want to go, maybe tomorrow. And also leaf theorists that are not that interested in VOAs are a priori, I think, quite interested in these questions, just because why not, right? They're interesting, they're difficult. That's what you want.
Oh, thank you very much.
Yeah, you're welcome.
Okay, are there any more questions?